Welcome back. In this video, we're going to be discussing helical gears and the forces that are transmitted through them. So a helical gear is similar to a spur gear, except that the teeth are at a helical angle with respect to the central axis of the shaft. So in this picture, Z is the central axis, the axis that goes through the hole in the middle of this gear, and there is some angle with respect to that, which is the helical angle. So the helical gears are great because they allow you to get more surface area of a tooth to have that line of contact, and it allows you to have for more gentle engagement. So we'll see lots of helical gears. So the things that make helical gears unique and how we usually specify them is by their helical angle. This is their helical angle, their normal pressure angle, and this is normal with respect to the tooth itself, not with respect to the z-axis. To be respectful of the z-axis, what we actually need is a pressure angle that is tangent to that. So depending whether we're talking about going around and counting the number of teeth that we can actually physically count, we're going to have n number of teeth, or if we're talking about looking at how effective this is, we may have an effective number of teeth. So we can talk about the teeth that are physically there, the ones we can count, as well as the effective ones when we consider the transverse pitch. So typically we'll see a gear specified by its normal pitch, its normal pressure angle, the number of teeth it physically has, and the helical angle. And those are the types of things that you'll typically see in a catalog, and that's what we'll have to work with. However, to understand how the forces are transmitted across this gear, we'll have to understand the relationship between some of this normal and tangential, or transverse. So there's basically a little bit of trigonometry involved here, but the things that are going to be useful for us is that the transverse pitch, the pitch for the actual gear engagement, is equal to the normal pitch, which we'd see listed in the catalog, for example, multiplied times the cosine of the helical angle. So this is the transverse pitch. And when we're using pitch in our equations to describe the forces acting on the gear teeth, we're going to use the transverse pitch. We may also want to know what the transverse pressure angle is with respect to the provided nominal angle. So that relationship looks like this. The cosine of the helical angle is equatable to the tangent of the normal pressure angle divided by the tangent of the transverse pressure angle. So depending on your what you're looking for, typically you know the helical angle and you know the pressure angle. These are specified for a gear, and what you're looking for is actually the transverse pressure angle. All right, so doing the trig based on those, we can see that there's some W force acting down on our gear, and it's going to have three components, and these three components are the thing that we've used to before, WT, that's the one that's actually transmitting the torque. It is also putting the gear tooth in bending. There is the radial component, which pushes the shaft down and pushes into the gear, into the tooth. And now we also add to that an axial portion, which tends to want to slide the gear along the shaft. So it puts the shaft in axial loading. So what this looks like for most our situations, again, it's easy to find the WT and we'll be interested in what the WR is and WA is with respect to that. So if you have a tangential load, you can multiply times the tangent of that transverse pressure angle and find your radial load. And same thing with the axial. You can take your tangential load and multiply it times the tangent of the helical angle. And you'll come up with what is the response in the radial and axial directions to that load. All right, so recall for helical gears, we had this concept of virtual teeth. Where n prime, number of virtual teeth, is the actual countable number of teeth divided by the cosine cubed of the helical angle. So this is mainly used in the Lewis bending factor, in finding the Lewis bending factor. And the reason is the Lewis bending factors are based on spur gears, and helical gears are not exactly like spur gears. We will also be concerned with the minimum number of teeth it takes for helical gears not to interfere. So the smallest number of teeth on the pinion is related to the depth of the cut of the teeth, as well as the pressure angles. So this relates the angles, the pressure angles, as well as the ideal gear ratio R here. Again, the Shigley book uses M, but that's a little confusing with the module, so I've replaced it with an R. All right, let's see how this works in a similar problem to what we've done before. So this is a problem that builds on what we've had before, but instead of spur gears, now we're going to look at helical gears. And specifically, the issue we have to deal with helical gears is, as well as radial forces, which we're going to need bearings to resist, we're also going to now have thrust loads, which our bearings are also going to need to be able to resist, as well as it's important where we put those thrust bearings to make sure that we're keeping our shaft in compression. So it tends to be that a shaft in compression does not fail as often. So if we've got bending loads that cause tension, things tend to fail in tension. And then we add to that more tension of our thrust load, we're working against ourselves. It would be better to put that thrust load and make the shaft be in compression and get more strength out of our shaft that way, or counteract some of the tension due to bending. So let's look at what we have. We have a pinion at 2, which is described like this. It is right-handed. It has a helical angle of 30 degrees, a normal pressure angle of 20 degrees, and 16 countable actual teeth. The normal pitch is 6 teeth per inch. Now for the gear, which is number 3, so this is number 2, this is number 3. Gear 3, if it's running in parallel, it must be a left-handed gear if they're facing the same direction. So if you want to run a right-handed helical gear on a right-handed helical gear, you're going to be 90 degrees. The shafts are going to be perpendicular to each other, but if you do opposite-handedness, then they can be parallel to each other. And gear 3 is obviously going to have the same helical angle, otherwise the gears won't mesh. It's going to have the same pressure angle, otherwise, again, the gears won't mesh. It needs to have the same normal pitch, and it'll have the same, of course, transverse pitch. The only difference then is that the number of, again, countable actual teeth is 42. The input power is 25 horsepower. Pretty big, decent-sized small motor. and that's spinning at a speed such that the pinion is spinning at 1720 revolutions per minute. Alright, so what we want to know is what are the reactions on the bearings, and that's what we're going to be figuring out based on the gear forces. So first things first, we're going to need to figure out what the gear forces are. So first of all, we're going to need to be working in a transverse direction. So everything that we have so far is normal to the direction of the teeth, which is at an angle to the shaft. What we'd like to know is what are the forces and pitch and pressure angles with respect to the axis of the shaft. So we're going to consider things in the transverse sphere first. So the transverse pressure pitch is, of course, the normal pitch multiplied times the cosine of the helical angle. So for our situation, that gives a transverse pitch of 6 times the cosine of 30 degrees, or a transverse pitch of 5.196 teeth per inch. So the transverse pitch is going to be a little bit less than the normal pitch. And this makes sense because we're getting more teeth around the circle than we would, because they're at an angle, than we would if they were just normal. So the transverse pitch and the normal pitch of a spur gear when the helical angle is 0 are the same thing. So the transverse pressure angle is related to the normal pressure in the helical angle, as we mentioned before. And we can do the inverse tangent of the tangent of the normal pressure angle over the cosine of the helical angle. Plugging in our numbers of 20 degrees and 30 degrees, we have a tangential pressure angle of 22.8 degrees. This is a transverse pressure angle with respect to the z-axis, the one that goes through the center of the gear. Alright, now we can start to understand how our forces are actually acting. The pitch diameter of the pinion is going to be the number of teeth, which was 16, divided by the transverse pitch. So for our situation, that was 5.196. This gives us a diameter of our pinion of 3.079 inches. And we can do the same thing for gear 3, which had 42 teeth and 5.196. Again, it's going to have the same pitch, which gives us a diameter of 8 inches and a little bit, 8.083. So now we can find the pitch line velocity of the pinion or the gear, because they're interacting with each other. Recall that is pi times the diameter times the speed over 12 to have feet per minute. So of course this equals pi times 3.79 inches, and then the speed. So if you're using the gear, use the speed of the gear. If you're using the pinion, use the speed of the pinion. In this instance, we're using the pinion, so it's 1720 divided by 12. That gives me a pitch line velocity of about 1,386.5 feet per minute. Then we can use our gear equations to understand what is the transmitted load being transmitted at that power. So recall we have 33,000 horsepower over velocity, pitch line velocity, and that gets us 33,000 times, in this case 25 is the horsepower, and our pitch line velocity of 1,386.5. This results in a load of 595 pounds. Excellent. So now we know the force that's being transmitted between one gear and the other. But now our question is, what is the loads in the radial directions and the axial directions as well? So recall that our axial force is relatable to our tangential force as 595, that's the tangential force, times the tangent of the helical angle. So that's going to be about 344 pounds. Same thing for the radial load. We're going to have the tangential load, 595 pounds, but this time multiplied times the tangent of the transverse pressure angle, which is 22.8, such that our radial load is 250 pounds. Now you can do this whole process again for the gear, but ideally you're going to find the exact same values because these forces are equal and opposite since two gears are interacting.
Alright, that'll about do it for this video. Until next time.